I've learned string theory from the Polchinski and a little bit of some conformal field theory books, like the Di Francesco. Most of what I'm going to tell you during these lectures can be found in those two sources. There are many other textbooks of string theory and lecture notes and available online. I've not read them, so I don't quite know which others to advise you to use. Now, the tone of the lectures will vary a bit. Sometimes they'll be a bit more descriptive. Sometimes they'll be more technical. Some of the technicalities are just unavoidable in defining string theory. I'll try to focus on technicalities which are useful, which are really technicalities about quantum field theory. So they should be useful for you beyond studying string theory. Now, essentially, almost all that we're going to talk about during these lectures is perturbative string theory, meaning it's something analogous to the perturbative expansion, the expansion in Feynman diagrams of the quantum field theory. There are possibly ways to do better than that in the sense that, I mean, in quantum field theory, usually you have a full, more or less rigorous non-perturbative definition, and the perturbative expansion is something derived. In string theory, we start with the perturbative expansion, and finding a good non-perturbative definition is sort of tricky, although it's probably possible to radiate CFT. But that would bring us too far for the amount of time that we have available. Now, in order to understand the perturbative expansion of string theory, it's useful to just look at the quantum field theory perturbative expansion again, trying to get a physical feeling of what does it mean, what a Feynman diagram means. So suppose you have some simple scalar field theory, like a 5 to the 4th theory, something like that. Okay, so you want to compute some amplitude, something like a scattering amplitude. You know, a bunch of particles coming in and going out. And you do it in the perturbation theory, you do it by summing over Feynman diagrams, loop by loop. So you sum over a certain class of graphs with some coupling. Some other numbers. You sum over, and then what you do, so you take your graph, and you build an amplitude for that graph. Say, there's something that looks like this. You're going to take the product of propagators. Over the edges of your graph. And some momentum conservations at the vertices. Something like that. Now, this amplitude usually comes from some sort of a path integral, an integral over the histories of your quantum fields. Now, it turns out that, in a sense, each of these amplitudes associated with the Feynman diagram is accounting for all the histories which have a certain shape. Now, to make this precise, well, or more evident, you can use something called Schwinger parameterization. So you can write your propagators like this. So you introduce a proper time for each of these edges. After you do that, then everything becomes Gaussian in the momentum. Oh, I guess I should put some integral of the momentum. Of course, you can also write the vertices can add a bunch of auxiliary variables. You can add some proper times on the edges. So let me just write it bigger. And some positions on the vertices in space-time. Okay. Now your integrals of the momenta are Gaussian. You can just integrate them away. You get something like attached to each edge. Let me call it the edge between points I and J. You get something like this. Okay. So we have rewritten our Feynman diagram a little bit. Now it's an integral over the proper times, an integral over the position of the vertices. And then the product of these functions. There are a bunch of other extra factors, but I mean, here there is probably something like 1 over square root of tau ij and so on. Don't trust my formula in general. So, and it turns out that this can also be written as in an interesting way. It's actually the result of a quantum mechanics path integral. I will show you the details momentarily, but for now, let me just say that there is some action such as if you do your path integral from 0 to this time, and with initial positions fixed by the endpoints of the edge. Okay. This can also be written as an integral of histories, the histories of one particle. Okay. So this whole Feynman integral became this whole diagram. The amplitude for this diagram becomes an integral over some intrinsic shape, some intrinsic geometric shape of your diagram, the intrinsic length of your edges. And then an integral over all possible ways, this diagram has been embedded in space-time. So you pick the lengths of all the edges, then you pick where the positions of the vertices are, then you integrate over all the possible ways a particle can go from this point to this point in this proper time. So the way Feynman diagram is really a small, it's not anymore a quantum field theory path integral. It becomes a quantum mechanics path integral for each edge. So your particles propagate freely between the vertices. And then there are these interaction vertices we put by hand, where we prescribe how particles can appear and disappear. Now, so let me just okay. So to get our amplitude, so we do two things. We integrate over the intrinsic geometry of your diagram, and then you integrate over all the ways that diagram is embedded. So to define string theory as a perturbation theory, we're going to do pretty much the same. Does this actually move too? Or if I cycle it in? Ah, cool. Okay. So so you want to study strings. It means that they are not point-like objects. They are objects with one dimension. So the history of a string is a tube. So instead of a Feynman diagram like the one I draw above, you have something that looks like this. Bunch of tubes coming in, going out. Now, the main difference between strings and particles is that for particles, I had to put the interactions by hand. And there is a lot of freedom in doing that. Now, in strings, I could, I guess, also try to put by hand some interactions. But there is one particular choice, which has a particularly nice feature, which is I don't do anything especially dramatic. I just let everything join smoothly. Into some big surface in space-time. And essentially, the fact I'm not doing anything dramatic at specific locations is the reason string theory ends up being much better behaved at large energy or small distances than quantum field theory does. So the basic reason string theory can describe, say, a theory of quantum gravity without UV divergences is because all interactions have been smeared around a little. There are other reasons, but this is one important reason. Now, in order to compute the amplitude, we're still going to integrate over the possible intrinsic geometry of this Riemann surface, or this surface. And then we're going to integrate over all the possible ways this object can be embedded in space-time. So now before continuing, it's probably useful to go back and show you how do you get this. Because pretty much the same, I mean, the derivation for string theory will be very similar. So we need to start with some action for a single particle moving in space-time. It's a line. So if I want to have something featureless, I don't want to add anything else to this line. Pretty much the only thing I can use for the action is the length of this line. So my action can start its life just as something like this. Now, in order to write this length in terms of the shape in space-time that this line has, there's a standard formula. You pick some parameter on your line, whatever it is. And we call it U. This is the length element. And I integrate it over the line. And I guess I can pick my parameterization, so it runs from 0 to 1 from that. I'm trying to study propagation from 2 points in space-time. Now, doing quantum mechanics with this, yes?
Is there a metric in intrinsic within what you're defining?
Well, I lowered an index, so I'm doing things I'm using some metric in the target. In the space-time, there is a metric, flat metric. I could, if I wanted to do a particle in curved space, I would indeed replace this with some metric in space-time.
So we throw out assuming that.
So we could do this. It makes very little difference but it makes the theory not free. You'll see in a moment. But yes, and now we assume Lorentz invariance, and we're going to assume Lorentz invariance also for string theory. Actually, that's another nice feature of string theory, that you can regularize short distance singularities and still keep Lorentz invariance. So Lorentz invariance does not need to be an emergent property at low energy. It's just there from the beginning.
Would you specify what you mean by intrinsic geometry? I mean,
yes, I will. I will. So now it's pretty hard to work with square roots of something in your action. So we are going to add the Lagrange multiplier to make it easier. So we have some new variable. We call it E. So I'm going to have our path integral will now be an integral over x of u and E of u. And we write the action in this form. I might say that I've gained little. Okay, I don't have a square root anymore, but I have 1 over E. But this action actually has a nice symmetry. So this action was reparametrization invariant, meaning if I change from u to some new variable, E prime of u, your derivative is transformed by the usual factor, the u over the u prime, comes out of the square root, and cancels against the Jacobian of the integral. As long as this transformation is monotonic, at least, this should be fine. And even if it's not monotonic, as long as you extract your square root properly. Here there is still the same symmetry, but you need to transform E as well. So I want E the U to be invariant. So I do something like that. Okay. So in a sense, the original action had a big gauge symmetry. Okay. It was supposed to be an action over all possible paths in space-time. But I introduced a new freedom in picking the parameterization, picking a coordinate along these paths. This was an extra thing that I put in, and I had to take it away sooner or later. So the way you take it away is by treating this as a gauge symmetry. And now this gauge symmetry becomes like this. Now is a good time to get rid of this symmetry by gauge fixing it. So we pick a gauge. Pick a gauge in which E is actually constant. I can always do it by picking my coordinate appropriately. By gauge fix, I cannot quite set E to 1, see, because although I have this freedom, the integral of E the U is gauge invariant. The integral of E the U is gauge invariant. So let me call it tau. So I can get rid of almost everything, of all the time-determinate parts of E, but I have to leave the overall scaling, the whole length of this line. So my path integral was started its life as in path integral over dx over the gauge symmetries. Then I put in this E. I got rid of most of E by getting rid of gauge symmetries. And I'm left with the integral over tau. So my action now looks like the integral from 0 to tau of dx mu over du, dx mu over du, plus m squared. So now I'm pretty happy because this is quadratic. It's a free action. So I can finally do my path integral exactly as Gaussian. And the result is this one up there. Okay. So,
So you're saying that both actions give you the same equations of motion at the end?
I'm saying actually that the path integral for both actions is the same. Although defining the path integral for this action is going to be sketchy. So what I'm really saying is that you should take this as definition of that path integral. But if you could give a good definition to this path integral, then it would be the same as that. Okay. Now, right, so here I did the gauge fixing a bit by hand, okay? Strictly speaking, I should have introduced ghosts and done, BRST symmetry, all of that I'm sure you guys have seen in one of the last lectures on gauge theory. But I will go over it again in a couple lectures. But for now, let's just do gauge fixing by hand. It's fine. Okay. Now, here I did a scalar theory. But it's not difficult to extend this to more complicated quantum field theories. For example, if you want to have a nice exercise, you can try to do fermions. Start with the Dirac propagator and try to rewrite it as one-dimensional quantum mechanics. So the trick is that when you study more complicated theories with more complicated choices of particles, all that you have to do is to make this quantum mechanics a little bit more complicated. For example, in the case of the fermion, you might find that if you add some Grassmann odd variables, which are partners of the positions, these are going to give you after quantization the gamma matrices that you need to write down the propagator. In a similar way, if you add some very trivial quantum mechanics, which say has just two levels with energy M1, energy E1 and E2, you'll end up with two copies of this scalar theory. I mean, with two types of particles whose mass squared is exactly that E1 or E2. So in general, if you add some extra quantum mechanical degrees of freedom to your particle, you can get multiple particles in your quantum field theory. Now, when you study a string, you see, a string has a lot of extra degrees of freedom besides the center of mass moving around. A lot of vibrational modes, like a lot of harmonic oscillators placed on top of your basic center of mass movement. And that means that those extra degrees of freedom end up meaning that you have a lot of particles. So a string ends up being more or less equivalent to a lot of particles, of towers of particles with increasing mass. And at least at low energy, at least below a certain scale, string theory really looks like just a quantum field theory. If you look at this picture from very far away, you just see some lines coming in. You don't see the string anymore. And so the fact that string theory just naturally goes to quantum field theory at low energies is really crucial. And actually, of all these infinite towers of massive particles that appear when you quantize the string, only the very lightest modes, the massless particles, are the ones that really control the behavior at low energy or large distances. So string theory is going to give essentially quantum field theory at low energy, but a quantum field theory which happens to contain a graviton, maybe some gauge fields, fermions, depending on which kind of string theory you're looking at. So it ends up giving all the sort of ingredients which we see in quantum field theories around us. And this is the first reason people really got excited about string theory, is because it naturally produces all the ingredients that you need to make a quantum field theory of what we see around. Now, which ingredients do you get depends on exactly which degrees of freedom you put on this string. And well, anyway, we'll see. But some are always there. For example, gravity is always there in string theory. And we'll try to understand why is that the case. OK, so now I would like to essentially repeat this game, but do it with a string. So what do you do? So for a particle, we said the natural action was the length of the line. So for a surface, the natural action is going to be the area of the surface. OK, so I pick again some coordinates on the surface, U1 and U2. This is the area element. So this integral gives me the area of the surface. Again, this equation, I introduce some extra degrees of freedom in picking a parameterization. And there is a reparameterization invariance. I can redefine the U's, define new U's in terms of the old U's. And the answer will not change. So infinitesimally, this is written as delta UA equals some dA of U1. So these are the gauge symmetries of this action. And we would like to make sense of some sort of a path integral over all these possible maps over reparameterizations.
I'm not sure it's clear what surface, the area of what surface you're talking about, and also what is T.
This is the surface.
Maybe you can say a few words.
OK. Well, I mean, as I said, we're trying to compute this, the amplitude for this process to happen, where a bunch of strings are coming in, a bunch of strings are going out, and they form a surface in space-time. So I'm trying to do things in parallel to what we did with the particles. So in the particles, we got the propagator. We got everything out of studying the possible trajectories of these particles, integrating over the trajectories. So we need an action for the particles. We computed the two-point function. Now, as I said, there I needed to do things separately for each segment of my graph. But here, everything is joined smoothly. So I can just do everything altogether. I can just pick this surface and try to ask what happens if I integrate over all possible surfaces e to the minus area of the surface. Because pretty much I don't have anything else. I didn't put anything else on that surface, so all I can use is the area.
You've given the dimension of space-time general, right?
Yes. Yes.
Any particular reason by choosing the dimension of the surface to be 2?
Because I'm doing string theory. If I was doing some, well, ultimately, I can. This game I'm playing now, I can do for other dimensions of the surface of the object, but it gets stuck very soon. There's something special about 2 dimensions, which we'll see momentarily. So unfortunately, we don't know how to do membrane theory, which is a pity because presumably that would give them theory, perhaps. So I'll get in a moment to see what's special about this when I have only 2 of these coordinates. Okay, so say it again. So x, this field x mu. Okay, so this u1, u2 are coordinates on my surface. These x1, u2 are just maps from this surface, and we call it sigma, into space-time. And I want to somehow do a path integral over all of these maps up to reparameterizations of the U's, of the local coordinates. Now, I can try to repeat the trick I used up there. So I introduce some auxiliary variable to try to make the square root go away. Now, this is called the Namugoto action. The action which makes it quadratic is called Polyakov action. So that is, you add a metric, a choice of metric on your surface. Now, if you look up here, we were trying to, ultimately, we more or less interpreted tau as a proper length of your edges. So you see that E squared was pretty much like a metric on your line. So now, you pick a metric on the surface, and we write the action. I mean, once you put a metric on the surface, you want your action to be invariant under reparameterization. Again, there is not much freedom. So the most natural thing you can write is this one. Okay. Now, it turns out, although it's a bit tedious to show, that if you integrate away h, at least classically, if you extremize with respect to h, with respect to this metric, you recover this action. I mean, it's straightforward, although a little bit tedious. You need a sort of formula that you might have seen in general relativity for doing derivatives of the inverse metric with respect to the metric. Things like this. I'd probably get it wrong, but symmetrized. And so on. But you can do it as an exercise. The point is, so this action still has your reparameterization invariance. The metric is transforming the usual way the metric should transform. Essentially, in such a way that the length element remains constant. And starting from this sort of transformation, you can see that this is invariant under reparameterization. Pretty much the transformation of the metric cancels out the transformation of the derivatives. H, as usual, is the determinant of the metric. So the transformation of the determinant cancels out against the Jacobian. So, okay. Now, what's special about two dimensions? What's special is this action is an extra symmetry, which is called Weyl invariance. So if you take your metric, you just rescale it. Without doing anything to your position coordinates. This gets a factor of e to the minus phi. This gets a factor of e to the phi. It cancels out. So this means that if you want, it means that if you try to do this, we're not going to get infinity right away. Because the action does not depend on the choice of scale of the metric. So we're going to get the integral over this scale factor gives infinity. So to do string theory, you actually divide also by this sort of Weyl transformations. These are the Weyl transformations. Just rescaling of local rescaling of the metric. If you think about it, it's a very strange symmetry. Notice this is just the theory of a free boson in two dimensions, coupled to some metric on the surface. We're learning that the theory of a free boson in two dimensions, massless free boson, does not seem to change if you change completely your metric. So this can get a space that is flat and make it into a tube, make it into a ball, make it into a completely weird, bizarre shape. But somehow the correlation function of a free scalar are supposed to be not affected by those transformations.
Why is the Weyl transformation not a subset of diffeomorphisms? Because isn't it equivalent to just rescaling all of your
Well, because I'm not touching the coordinates. Also, I'm not touching this x's. So while I do this, I leave x to x. I'm not touching those. Now, this Weyl symmetry is actually quite convenient because, see, in one dimensions, we had extra degree of freedom, and we had one reparametrization, so we could just get rid of this new degree of freedom. But the metric in two dimensions has three components. But I only have two diffeomorphisms. So if we didn't have Weyl symmetry, we would be left, we will not be able to sort of gauge fix away the metric completely. We will be left with some free remaining part of the metric, which would make the action very complicated. So the metric would be something like a new degree of freedom, really dynamical with a very complicated action. But this is Weyl invariant. And there is a nice theorem that at least locally, you can start with any metric you want, use diffeomorphisms and Weyl transformations to make it flat. Now, globally, that's not exactly true. So globally, there is a little bit of extra freedom left on how you glue together these different flat patches of the metric. And we will see later it has something to do with something called the complex structure of the surface. Pretty much, it has to do with the fact that if you pick your gauge so that your metric is flat, just use it. And you go to complex coordinates. So the geometric becomes the z bar. Okay. Now you can do a complex, an holomorphic change of coordinates. Your metric will become just like that. So crucially, complex coordinate transformations, holomorphic coordinate transformations, just multiply the metric by something, which means they can be eliminated by wild transformation. So if you try to throw away as much as you can of the metric by using wild transformations and diffeomorphisms, so if you try to gauge fix everything by saying, I want the metric to be flat, I can do it in some patch, I can do it in some other patch, but the different choices I make might be still related in different patches, but by holomorphic changes of coordinates. And it turns out that by gluing together flat matrix with complex coordinate transformations, I can actually still make very interesting surfaces. Or vice versa, if I'm given a complicated surface like this, I can patch it up from a bunch of flat pieces of flat space with some of these holomorphic transformations. Now, for a while, we'll.
Can you repeat that part? So, I'm not entirely sure what the non-triviality in that is. Are you?
Suppose I give you a sphere. Okay, for some reason, I want to do a path integral on the sphere. Okay, this is not a sphere, but suppose it, for some crazy reason, I wanted the surface to be just a sphere. Or even better, some complicated, like a pretzel. Okay? Now, there is no flat metric on the pretzel. There is no way to make the pretzel flat everywhere. For example, you know that the integral of the curvature over the whole pretzel is a constant, which is called the genus of the pretzel. And this has genus 3. Okay? So you cannot get 3 by integrating 0. So the pretzel cannot be made flat everywhere. But what I can do is to break the pretzel in chunks, make the metric flat on each chunk of the pretzel, and then patch it up by this sort of transformations, which allow me to glue together flat pieces of flat metric in a non-trivial way. So this is a valid operation in this context because, see, the action is well-defined on one patch, it's well-defined on the other patch, and the action on the two patches agrees because I'm going from a patch to the other by a diffeomorphism together with a wild transformation. So I can glue together this local calculation globally, and it makes sense, at least classically. Now, in quantum mechanics, there is going to be some issues. Yes?
Sorry, I still don't quite get that. How we can make the metric that by changing the variable from the V1, V2 to the complex V.
No, I'm saying make it flat. So there is a theorem. It's a difficult theorem of analysis. That given any metric, you can make it flat with the diffeomorphism and the wild transformation. It's a theorem. I'm not going to prove it to you. I don't know how to prove it. Locally, it's kind of intuitive because there are 3 degrees of freedom in the metric. I have 3 degrees of freedom to play with. But
Okay, so and what is the purpose of going from V1, V2 to the complex coordinate?
it's just to show you that although once I make this operation, make the metric flat, I did not fix my degrees of freedom completely. So if you make the metric flat here, and I make it flat, and then we compare nodes, we might discover that we didn't make it flat the same way. But our choices of coordinates differ by an holomorphic change of coordinates. Okay. Now, luckily, okay, let me leave it at that. So once I make the metric flat, I can get rid of almost, I can get rid of h from this, and my action will just become something very simple. Okay? So my path integral over the x's became Gaussian. It's all trivial, free field theory on my surface. Same as it happened for the particle. So calculations would be actually pretty straightforward. Yes?
So you're saying at the level of the action both are equivalent, right? If I make a transformation such that locally my metric is flat. But if I just calculate, for example, the equations of motion for this action, then I have extra structure than for just free field theory, right?
No.
I don't have more constraints on my equation.
Wait, sorry, yes. Sorry. I'm doing a gauge fixing, so I still had to pay the usual prices of doing gauge fixing. So for example, I got rid of h, but it's true. The equations of motion for h would still have to be imposed. Okay. Like the Coulomb constraint in gauge theory. So it's perfectly true. I had to work with this action and at the same time also impose the s over dHAB, which is the stress tensor in 2 dimensions, to be 0 classical. We had to figure out how to impose this quantum mechanically. But there is, it's not different from what you're seeing in gauge theory, where you had to impose current conservation after you gauge fix. Now, the true problem is that, as I said, this is all classical, and while symmetry, so which means that if you want to actually make things work, I better make sure that these symmetries are symmetries not just of my action, but also of my measure in the path integral. Now, it's possible to make the measure invariant under reparametrizations. After all, they're just changes of coordinates. How do you regulate the path integral usually? Typically, you expand your fields in some modes, and then you truncate. You throw away all the modes beyond a certain point. And say you can throw away all the modes which have a fluctuation which is faster than something. And you can measure how fast is this fluctuation just by using the metric itself. So if you do that, there is no dependence on your condition on the actual choice of coordinates. So it's easy to define your measure in a way that is invariant under diffeomorphisms. But to do so, you use the metric. To regulate, you need some notion of distance. You need to throw away the modes which are moving too fast, have too much energy. So if you do it in a way, if you define your cutoff in a way that depends on your choice of coordinates, then you're in trouble with diffeomorphisms. That's bad. If you define your notion of cutoff by using the metric, you're fine with diffeomorphisms. But you're going to be very careful with wild transformations which change the metric. And indeed, it turns out that if you regulate this in a way that is diffeomorphism invariant, it cannot be also invariant under wild transformations by itself. So if I take a free boson, it's not invariant, the measure is not invariant under wild transformations. So I'm in trouble. Now, we will kind of see that so this is what's called usually an anomaly. I have some symmetry of my classical action, but it turns out that there are troubles regulating the path integral in such a way that the symmetry holds true. And if the symmetry doesn't hold true, then I cannot gauge it. So typically anomalies happen for some topological reason. So it can be rather hard to wrap your head around them until you have done a few examples, because depending on how you regulate your theory, you'll see the anomaly, the problem pop up somewhere. You say, oh, okay, I messed up. I regulate it differently, and the anomaly pops up somewhere else. You can squish your measure in many ways, but the anomaly always pops up somewhere. So there's something topological about it. Just it's really like trying to make something like this flat. You can, but you can do it locally. So on the other hand, because it's topological, it turns out that it can be captured by relatively little information. At the end, there is just one number which characterizes how not Weyl invariant a measure can be. So under Weyl transformation, this measure transforms in a certain way, and the failure to be Weyl invariant depends on some number, which is called the central charge. Each of your coordinates in space-time contributes something to this central charge, 1, say. And then the integral over the matrix contributes something else, which happens to be for minus 26. So if you put 26 coordinates in your space-time, the anomaly cancels, and this makes sense. So vanilla string theory, bosonic string theory, works if you put 26 coordinates in your space-time. If you don't put them, then the Weyl transformations don't decouple. You try to get rid of the metric, but you're still left with the Weyl with the dynamics of this conformal factor. And, well, you get something else from what you wanted to get. Instead of getting something that looks like maps from your string to space-time, you get an extra coordinate with a funny action that comes from the Weyl transformations. You get something that can still make sense. It's called non-critical strings, but it's not what we're going to try to discuss for the rest of the lectures. Questions? I saw some hands.
Yeah, so you said that we cannot simultaneously ensure diffeomorphism and variance while symmetry.
Yeah. Actually, the full statement is that you cannot ensure Weyl invariance, diffeomorphism symmetry, and Lorentz invariance. Okay. There are ways to squeeze things around so that it looks like you got Weyl invariance and diffeomorphism invariance, but because you screw up one of the coordinates of space-time, or something like that. So.
Okay, so the procedure we adapt, we usually hold on to Lorentz.
Yes.
And diffeomorphism.
Well, it depends. It depends. So if you look at if you read Polchinski, there are a bunch of different quantizations. There's something called light-cone quantization, in which you pick two coordinates and you treat them different from the others. Essentially, you use your two diffeomorphisms to gauge fix those coordinates instead of gauge fixing the metric. And then the metric drops out by itself. All is nice and fine. There are no ghosts, nothing to worry about, except that Lorentz invariance is broken unless you have 26 dimensions. Yeah. So right, in these lectures, I'll just try to do it in one way. So I'll keep Lorentz invariance. I'll work with some ghosts. And
so is it equivalent? Like, so we've essentially got these three things that we're trying to preserve in some sense.
Yes.
So you pick any two while you're varying the. So your path to quantization in terms of the three possible combinations that you have.
Mm-hmm.
Of two at a time.
I'm not sure I would.
To the same theory and converge to the same thing?
If you're in 26 dimensions, yes. But because it's all gauge fixing, see? And it's possible, usually if you do things properly with ghosts and BRST symmetry, it's possible to show that different gauge choices are equivalent. We'll actually try to see why that happens. Now, yeah. You see, all right. Typically, so gauge choices which let you end up with a free action are usually preferable because it means that you can actually do calculations. In principle, if you had an oracle that knows everything about two-dimensional field theory, you could make crazier gauge choices. You would get some interacting two-dimensional quantum field theory. And you could ask the oracle to solve it for you and still do string theory. But it's nice that there are gauge choices where things are actually free on the worldsheet. At least for flat space in the target, if you want strings moving in flat space. If you want strings moving in other spacetimes, then things are not free, and they can get more difficult. Okay, we are pretty much done. So let me see.
I'm just trying to wrap my head around this gauge fixing. So, for example, in QED, we had two ways we went about it. We said when we're trying to quantize, either we restrict the operators in my Hilbert space, or I first find the classical solutions that I restrict my classical solutions and then quantize those. Is there an analogous thing to what you're saying here?
Classical.
So the difference being between the Coulomb gauge and the Lorentz gauge way of doing it?
I mean, both Lorentz gauge and Coulomb gauge are the same kind of gauge fixing, right? You impose some conditions to kill your gauge degrees of freedom.
Well, I agree, but in one case you restricted your Hilbert space after, like you allow for all classical solutions and then you quantize and then say, okay, this operator acting on some states is going to...
I mean, if you want to do it properly, you use BRST quantization in both gauges. Now, sometimes there are shortcuts, but
why would it be bad if we still had anomalies? Like, why are we seeking for a quantization method that doesn't have anomalies?
Sorry, why are we seeking?
So what would go wrong if we still had an anomaly in our field theory?
Well, so it just means that I cannot divide by while. Okay? So now after I gauge fix, my path integral will be a path integral over the x's and over this while factor. Okay? This is like if you look at it's actually possible to compute what is the failure what is the transformation of this measure under while transformations. So it looks like something like it's almost like a free boson plus something that looks like this, roughly. So what you end up with is a theory of a string moving inside this space-time together with an extra direction with a funny potential on it. It's fine. It's fine. I mean, unfortunately, see, bosonic string is sick by itself. We'll see in the next lecture that bosonic string is only a toy model. And this is the same kind of sickness. When you do superstrings, you can cure that sickness for bosonic string. Curing it for this kind of strings is a little bit, it's possible, but you end up with something that has only 2 dimensions. It's not very interesting. I mean, it's interesting for mathematical purposes, perhaps, but not much for describing the universe. Any more questions?
So we insist upon while invariant because it's more like it's just an insistence we have that our theory should be scale invariant.
No, because it gives something interesting.
What is that?
I mean, it gives an interesting string theory. The only reason at the end for which you do this is what you get at the end. If it gave something uninteresting, you would say, oh, while invariance was a bad idea, or something like that.